Okay, hello, my name is Scott Bryan from Physical Electronics, and the topic of my seminar today is Applications of TOF-SIMS MS for Industrial Problem Solving. So I want to start by acknowledging my co-authors, Greg Fisher and Dave Carr from PHI, and Ida-san and Miyama-san from Oleic PHI in Japan. We introduced the MS 2 years ago at SIMS XXI in Seattle. And over the last 2 years, we've been applying it to a wide variety of industries. And what I'm going to do today is highlight some of the main areas where we've found it an extremely useful addition to TOF-SIMS. So first of all, industrial problem solving is a unique environment. In the industrial setting, some of the typical analysis that you do are listed here. At the central labs for a large company, what you would find yourself doing is failure analysis and a lot of analysis which is just comparing a good sample to a bad sample. Defect analysis is important, and then the creation and protection of intellectual property. So in these industrial type analysis, it puts a specific type of requirement on the analytical group. And first and foremost is what's important is the ability to identify unknowns. So often you are working with samples where you don't know the whole story. The information from the samples is not always available. For example, by the time the sample comes to the lab, it's gone through a whole series of processing steps, many of which might have been done at vendors outside of the company, and they don't share information on all the chemicals used in their processes. So it puts a premium on analyzing unknowns. The other thing in industry these days is ease of use and speed are very important. So many labs are operating with fewer analysts and more equipment. So a premium is ease of use and speed. So what is the role of TOF-SIMS in a central industrial analytical lab? Well, we've heard from many of them that TOF-SIMS is often a last resort. If you can solve the problem easier, you're going to do it. So if you can solve it with an optical or any other non-vacuum technique, you'll do it. And quite often, if by the time the problem comes to TOF-SIMS, the specific information has not been available with all the other analytical techniques they've tried. So the most important thing is identification and relative quantification. This is why before I mentioned good versus bad samples. And what people depend on TOF-SIMS for is adding additional specificity over techniques like XPS, Raman, IR, or SEM EDS. In other words, you might know something about the elements and the functional groups, but what they're looking for TOF-SIMS to provide is the exact molecular identification. And what I'm going to try to show you in this presentation is MS significantly improves our ability to do this. TOF-SIMS is shown here, where the secondary ions come from the sample, are accelerated through the time-of-flight analyzer and to the MS1 detector. So in the standard mode, we get our TOF-SIMS spectrum from the MS1 detector. So what's been added is after the 3 ESA sectors is a precursor selector where we can pick a single mass out of the MS1 spectrum, deflect it up through a collision cell, and detect the MS spectrum. So as you see here, we collect the TOF-SIMS spectrum at MS1 and the tandem MS spectrum at MS2 detector in parallel. The ability to switch between MS1 and MS2 is what we've worked on over the last 2 years. And it's become very, very easy. It's basically a push button on-off, whether you activate this cursor or not. So all you have to do is enter the precursor mass, turn it on, and you get an MS2 spectrum. And what I want to point out here is that MS2 operates at the same repetition rate as MS1. So there's basically no change to your TOF-SIMS conditions. So now let's move on to the case studies. So the first case study is the unknown identification on the surface of a commercial polymer. So the commercial polymer is polypropylene. The TOF-SIMS spectrum is shown here. And as you can see, above mass 200, there's just a whole host of molecular ions. So the challenge is to identify these unknowns. And the problem is it's difficult to identify them when you have a mixture of so many different molecules on the surface. So the way we've always done it in the past has been to use a TOF-SIMS reference library. So I show an example of that here. So if we're trying to identify the peak at 481, we'd go through our TOF-SIMS library and find 481, which is tinuvin 770, and try to match this spectrum to the unknown spectrum above. But as you can see, it's quite a challenge because the fragments from the tinuvin are just buried in the fragments from all the other molecules. And basically, besides the 481 and the 58, it's pretty difficult to find any of these fragments. The other problem is that the databases were generated a long time ago, and they're dominated by primary ions we no longer use today, such as gallium and cesium. And with the use of the cluster ion sources, the peak ratios are completely different in the reference library compared to what you would generate with a new TOF-SIMS today. So that adds another challenge. So by adding MS-MS, our job has become considerably easier. So here you see the MS-MS spectrum of the molecular ion at 304 and the molecular ion at 481. And the MS-MS spectra are much simpler than the TOF-SIMS spectra. And we can see that some of the fragments are in common between these two molecules, but some are unique. So to do identification, we turn to MS-MS spectral matching with the NIST MS-MS database. And it's good timing because this NIST database has been very actively grown. And as you can see, just this year they came out with a new version with 652,000 MS-MS spectra of 123,000 precursor ions. So that gives us a very large database to use for spectral matching. So if we try to use that database on 304, this is the result. Shown at the top is the TOF-SIMS MS-MS spectrum, and shown at the bottom was the best fit from the NIST database. And you can see the very, very good match of the major fragments. In the NIST database, there's 4 different search algorithms, and this was the #1 hit in all 4. So one thing I want to point out is this reference spectrum from the NIST database was acquired with an electrospray source in a triple quadrupole. One of the big benefits we have now is the ability to take advantage of the huge volume of data that's been generated in the traditional mass spec community and use it to identify our unknowns from TOF-SIMS. Here's the same spectral match routine with 481. Again, the NIST database easily identified the tinuvin 770. It was again the #1 hit on all 4 searches. This one was an electrospray with an Orbitrap mass spectrometer. But again, all the major peaks are the same. So moving on, case study #2 is visual defects in a commercial medical device. So in this particular medical device, there were black spots throughout on the medical device. On the balloon as well as on the tube here, it may be difficult to see. So here's a blow-up of an optical. They're just round black spots. And the suspects were the ink. There was two different printing processes on this same medical device, an inkjet printer on the pillow and a pad printing on this tube. So those are two different processes. So of course they were the initial suspects. So here's a TOF-SIMS Spectra, a negative ion mode, off the black spot and on the black spot, from 500 to 800 Dalton. And the obvious difference is this peak at 666 and 650. These two peaks showed up on the inkjet printed area on the pillow as well. So the initial blame was placed on the inkjet printing on the pillow. And just to be sure, the MS was acquired on both of these two samples, and the results are shown here, where we have the fragmentation pattern is identical on the balloon and on the pillow. So this was enough on this particular analysis to say that without any doubt that the cause of those black spots was the inkjet printing. Okay, case study number 3. Here, what I'm going to move on to is where MS has added some specificity to our assignment beyond what was possible with just standard TOF-SIMS. And in this case, we were identifying the inks, the dyes from red pen inks. So shown here was a sample white paper where one red pen was marked in a vertical direction, and then a different red pen was marked in a horizontal cross. These two pens, the Bic and a Staedtler pen, use different inks. So we want to be able to identify these two red inks. These two red inks are actually structural isomers. One uses Rhodamine B, which has a molecular weight of 443. The other one uses a Rhodamine 6G, and the two molecules are shown here. They have the identical mass, but they're simply different side groups. So it's a different arrangement of the same chemical formula. These molecules are very important in forensics and food chemistry. So shown here is the MS spectrum of Rhodamine B and Rhodamine 6G. And as you can see, the different structure of the molecules results in different fragments. We get a big 415 for Rhodamine 6G, and that's very small in Rhodamine B. And we get a very big 399 in Rhodamine B, and that's small in Rhodamine 6G. That's easily explained based on the structure. In the Rhodamine B, we have this functional group with a diethylamine, which undergoes, when it's collisionally activated, a loss of C3H8 to form this structure. Since this functional group is not present in Rhodamine 6G, that can't happen. Conversely, in Rhodamine 6G, we have this ethyl carboxylic group, which undergoes a rearrangement to lose 28 C2H4 to produce a carboxylic acid group. This can't happen in Rhodamine B because it's already carboxylic acid. So we can explain the differences quite easily, and that explains the loss of 28 and the loss of 44. We can then go further because just like in TOF-SIMS, the MS is an imaging technique, so we have images for every peak in the fragment ion spectrum. And so shown here is again the optical image, the total ion image from MS1, and as you can see, you can't distinguish the horizontal or the vertical lines. This is the MS2 for the 443, the precursor, and then the images of 399 and 415, differentiating the two structural isomers. Okay, case study number 4. Again, this is showing the added specificity that MS has brought to the analysis. In this case, we're looking at the double bond location for fatty acids in order to identify specifically which fatty acid is present. High energy CID enables what's called charge remote fragmentation, and this gives additional structural information. This was fully developed back in the 1980s by Michael Gross and his collaborators at University of Nebraska, and they showed the power of this method using FAB with high energy CID. And basically, when you have a long chain hydrocarbon, this unusual fragmentation occurs remote from the charge site. So if the charge site is some functional group here, like carboxylic acid or amide, the fragmentation happens in the hydrocarbon, and you get hydrogen elimination and the forming of these, a neutral and the fragment ion shown here. And the useful part is that this will happen on every carbon atom in the chain. So you get a series of peaks at every carbon atom unless you have double bonds or branching, and that interrupts this mechanism. We studied a series of carboxylic acids shown here, stearic acid, which is fully saturated, and then these three carboxylic acids, which just differ in the position of the double bond. They're all single unsaturated or mono-unsaturated polycarboxylic acids with the double bond at the 6th, 9th, and 11th carbon, counting starting from the carboxylic acid. So if you look at stearic acid, we get that nice, beautiful series of fragments going from all 18, you can count all 18 carbons in the stearic acid. In the oleic acid, it starts out the same, but then that's interrupted for the double bond. And what you can see is that from if I put the mass up on the stearic acid, starting from the precursor, all of the fragments are shifted by 2 compared to the oleic acid, including the precursor, but then after the double bond, they're the same. So you can clearly identify the position of the double bond. And then to see if that's consistent, we compared these 3 carboxylic acids, and that same trend held for all 3. So now we've added the ability to distinguish these 3 fatty acids from each other. So that's just a short summary of some of the measurements we've made over the last couple of years. And to summarize, the industrial problem-solving environment requires quick and easy unknown identification. The addition of MS to TOF-SIMS has dramatically improved our ability to do that. And the TOF-SIMS is now going to benefit from taking advantage of these large MS databases built from other ion sources and mass spectrometers. Okay, with that, I'll finish. Thanks for your attention.